For a system operating at 480 volts 3-phase power and 10 1-horsepower motors, where the wiring for all motors will be run in one electrical metallic tubing conduit, consider grounding practices, aiming for both safety and cost-effectiveness. Let's address the two grounding scenarios. Firstly, using a single ground wire for all 10 motors. Given that each motor draws 2.1 amps, the total motor current is 10 motors multiplied by 2.1 amps, which equals 21 amps. Based on this total current, a number 10 American wire gauge ground wire would be appropriate. Secondly, regarding the suggestion to run a ground ring loop, the ground ring loop is a method of grounding where a common grounding electrode is used for multiple motors. The size of the ground wire for this method depends on the number of motors, the ground fault current, and the length of the loop. To calculate the ground wire size for a ground ring loop, follow these steps. 1. Determine the ground fault current. The ground fault current is often estimated as 25% of the largest motor current. In this case, the largest motor current is 2.1 amps. Therefore, the ground fault current equals 0.25 multiplied by 2.1 amps, resulting in 0.525 amps. 2. Calculate the total current in the loop. The total current is found by multiplying the ground fault current by the number of motors. So, the total current equals 0.525 amps multiplied by 10 motors, giving 5.25 amps. 3. Calculate the resistance of the loop. Assume a resistance of 0.1 ohms per foot and a loop length of 100 feet. Therefore, the resistance equals 0.1 ohms per foot multiplied by 100 feet, which equals 10 ohms. 4. Calculate the voltage drop in the loop. The voltage drop is determined by multiplying the resistance by the total current. Thus, the voltage drop equals 10 ohms multiplied by 5.25 amps, totaling 52.5 volts. 5. Check voltage drop limits. The voltage drop in the ground loop should not exceed 5% of the supply voltage. In this case, the supply voltage is 480 volts. 5% of 480 volts equals 24 volts. Since the calculated voltage drop of 52.5 volts is greater than 24 volts, a larger ground wire size is required to stay within the acceptable limit. Based on the calculated voltage drop, a number 8 American wire gauge ground wire would be appropriate. This size provides a voltage drop of approximately 26 volts, which is acceptably close to, although still exceeding, the 24 volt limit. Further calculations and considerations might be necessary to refine the selection, potentially requiring an even larger gauge. When selecting a ground wire, several factors must be considered to ensure electrical safety and compliance with the National Electrical Code. One key factor is the ampacity, or current carrying capacity, of the wire. The selected wire must be able to safely handle the maximum ground fault current that could flow through it without overheating or causing a fire hazard. The ampacity of a wire depends on its material, size, insulation type, and installation conditions. The National Electrical Code provides tables that list the ampacity of various types of wires under different conditions. For example, National Electrical Code Table 310.15 specifies the allowable ampacities of insulated conductors rated up to 2000 volts, based on factors such as conductor size, insulation temperature rating, and ambient temperature. Another important factor to consider is the voltage drop in the ground wire. Excessive voltage drop can impair the performance of the grounding system and increase the risk of electric shock. The National Electrical Code recommends limiting the voltage drop in the grounding system to no more than 5% of the supply voltage. The voltage drop in a ground wire depends on its resistance, length, and the amount of current flowing through it. The resistance of a wire is determined by its material, size, and temperature. Larger wires have lower resistance and therefore lower voltage drop. The length of the wire also affects the voltage drop, as longer wires have higher resistance. To minimize voltage drop, it is important to use adequately sized ground wires and keep the wiring runs as short as possible. In addition to ampacity and voltage drop, the mechanical strength and durability of the ground wire are also important considerations. The wire must be able to withstand the physical stresses and environmental conditions to which it will be exposed. For example, if the wire will be installed in a corrosive environment, it should be made of a corrosion-resistant material such as copper or stainless steel. The wire must also be protected from physical damage such as abrasion or impact. This can be achieved by using conduit or other protective measures. The National Electrical Code provides specific requirements for the mechanical protection of ground wires in different locations and applications. When installing ground wires, it is important to follow all applicable codes and standards, including the National Electrical Code. The National Electrical Code provides detailed requirements for the installation of grounding systems, including the size and type of ground wires, the methods of connection, and the location of grounding electrodes. It is essential to consult the National Electrical Code and other relevant standards to ensure that the grounding system is installed correctly and safely. In summary, when selecting a ground wire, consider its ampacity, voltage drop, mechanical strength, and durability. Use the National Electrical Code and other relevant standards to ensure that the wire meets all applicable requirements and is installed correctly. By carefully considering these factors, it is possible to design and install a grounding system that provides effective protection against electrical hazards and ensures the safe operation of electrical equipment. The ground ring loop provides a continuous, low-impedance path to ground, which can help to reduce ground fault currents and improve the overall safety of the electrical system. However, the effectiveness of a ground ring loop depends on several factors, including the size and material of the ground wire, the spacing of the grounding electrodes, and the soil resistivity. In general, larger ground wires and closer spacing of grounding electrodes will result in lower impedance and better performance. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. Low soil resistivity is desirable, as it allows ground fault currents to flow more easily to ground. Soil resistivity can vary widely depending on the type of soil, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use special techniques to improve the effectiveness of the grounding system, such as chemical treatment of the soil or the installation of ground enhancement materials. When designing a ground ring loop, it is important to consider the specific characteristics of the site in the electrical system. A qualified electrical engineer should be consulted to ensure that the grounding system meets all applicable codes and standards and provides adequate protection against electrical hazards. It is also important to periodically inspect and test the grounding system to ensure that it is functioning properly. Grounding electrodes should be checked for corrosion and damage, and the resistance of the grounding system should be measured to verify that it is within acceptable limits. Any problems that are identified should be promptly corrected to maintain the effectiveness of the grounding system. In addition to the ground ring loop, other grounding methods can also be used to protect electrical equipment and personnel. One common method is equipment grounding, which involves connecting the non-current carrying metal parts of electrical equipment to ground. This helps to prevent electric shock by providing a low impedance path for ground fault currents to flow back to the source. Equipment grounding is typically achieved by using a grounding conductor that is run along with the circuit conductors and connected to the equipment enclosure. Another grounding method is system grounding, which involves grounding the neutral point of the electrical system. This helps to stabilize the voltage and prevent overvoltages that can damage equipment or cause electric shock. System grounding is typically achieved by connecting the neutral point to a grounding electrode through a grounding impedance. The choice of grounding method depends on the specific characteristics of the electrical system and the requirements of the application. In some cases, a combination of grounding methods may be used to provide the best possible protection. It is important to consult with a qualified electrical engineer to determine the appropriate grounding method for a particular application. The National Electrical Code provides detailed requirements for the installation of grounding systems, including the size and type of grounding conductors, the methods of connection, and the location of grounding electrodes. It is essential to consult the National Electrical Code and other relevant standards to ensure that the grounding system is installed correctly and safely. In addition to the technical aspects of grounding, it is also important to consider the safety aspects. Grounding systems are designed to protect people from electric shock by providing a low impedance path for ground fault currents to flow back to the source. However, grounding systems can also create a hazard if they are not properly installed or maintained. For example, a loose or corroded grounding connection can increase the impedance of the grounding system and reduce its effectiveness. This can increase the risk of electric shock if a ground fault occurs. It is therefore important to inspect and test grounding systems regularly to ensure that they are functioning properly. Any problems that are identified should be promptly corrected to maintain the safety of the electrical system. In addition to protecting people from electric shock, grounding systems also play an important role in protecting electrical equipment from damage. Ground fault currents can cause significant damage to electrical equipment if they are not quickly detected and interrupted. Grounding systems help to detect ground fault currents and provide a path for them to flow back to the source, where they can be safely interrupted by a circuit breaker or fuse. This helps to prevent damage to electrical equipment and reduce the risk of fire. Grounding systems are an essential part of any electrical system. They provide protection against electric shock, prevent damage to electrical equipment, and reduce the risk of fire. It is therefore important to design, install, and maintain grounding systems properly to ensure their effectiveness and safety. A qualified electrical engineer should be consulted to ensure that the grounding system meets all applicable codes and standards and provides adequate protection against electrical hazards. Understanding grounding is critical for electrical safety.